The life cycle of machine learning applications consists of two stages: model development and model deployment. While traditional machine learning systems focus on optimizing either model training or accelerating model inference, they often assume homogeneous infrastructure. However, real-world industrial deployment of machine learning applications involves hybrid infrastructure, including cloud data centers, local servers, containers, and serverless platforms. This paper presents StraightLine, an end-to-end resource-aware scheduler that schedules the optimal resources for different machine learning application requests in a hybrid infrastructure. StraightLine's key innovation is an empirical dynamic placing algorithm that intelligently places requests based on their unique characteristics, such as request frequency, input data size, and data distribution. This enables end-to-end resource-aware placement, reducing response time and failure rate for model deployment in heterogeneous computing resources. Machine learning applications have evolved from academic research to industrial applications, with use cases in anomaly detection, edge robotics, and autonomous vehicles. The life cycle of machine learning applications involves diverse resource requirements, such as graphics processing units for training and lightweight GPUs or CPUs for model verification. StraightLine offers a novel approach by considering the entire lifecycle, adapting to heterogeneous resources in hybrid infrastructure. The system consists of three layers: model development abstraction, multiple implementation deployment, and real-time resource placement. The StraightLine system is a hybrid infrastructure designed to optimize machine learning application deployment, focusing on streaming data. This system consists of three layers: model containerization, container customization, and real-time resource-aware scheduling. In the model containerization layer, NVIDIA Docker provides plug-and-go provisioning for model training and verification, ensuring stable and high-speed storage. Provisioned resources are automatically released when tasks are completed. The trained and verified models are compressed and serve as the foundation for ML applications. The container customization layer involves building RESTful APIs, serverless applications, and Docker containers tailored to different computing environments. Docker containers adapt to various environments, addressing software environment conflicts that may arise in hybrid infrastructure. In the real-time resource-aware scheduling layer, an empirical dynamic placing algorithm is designed to intelligently allocate resources for ML application requests based on their unique characteristics, such as request frequency, input data size, and data distribution. The algorithm aims to minimize latency and response time in the hybrid infrastructure. The model containerization process involves specifying CUDA devices, volumes, and libraries in NVIDIA Docker, creating a container with the required information. This approach enables high performance and stable model development. Container customization involves implementing containerized ML applications, which contain core information such as model weights and inference requirements, and can connect to specified target environments and resources. The real-time resource-aware scheduling algorithm investigates the frequency and data size of each request in the waiting queue, allocating resources based on request characteristics to minimize latency and response time. The empirical dynamic placing algorithm, outlined in Algorithm 1, optimizes the placement of a set of requests R across serverless, Docker, and Flask platforms. It considers request frequency at time t, request data size ROD, frequency threshold F, data size threshold D, and available resources of Flask SF and Docker SD. The output is the placement K of the set of requests R. The algorithm iterates through each request R in R, evaluating its frequency Ft and data size ROD against the thresholds F and D. If featuring exceeds F and ROD is less than D, the request is deployed on the serverless platform to offload the workload and minimize communication overhead. Requests with large data sizes are allocated to the Docker platform, which can tolerate longer response times. Requests with moderate data sizes are deployed using Flask if the request frequency is low, leveraging Flask's strength in providing lower response times. In cases where Flask is unavailable, requests with moderate data sizes are allocated to either Docker or the serverless platform, with priority given to Docker. The algorithm returns the placement K of the set of requests R. The efficacy of the proposed approach, StraightLine, is evaluated on a real-world hybrid infrastructure testbed, comprising a 2-node GPU-ready in-house data center and NVIDIA Docker equipment. Preliminary experiments demonstrate StraightLine's ability to reduce response time and failure rates for model deployment in diverse computing environments. The testbed setup is described in detail, including the computational resources and GPU configurations used for model deployment in the hybrid infrastructure. The experimental setup for this research paper consists of a local web server with 12 cores of Intel Xeon E2176M CPU, 32 GB of memory, and serverless computing on AWS Lambda with 5 GB memory. TensorFlow is used as the ML application runtime, and Flask exposes it as a RESTful API. The web server is hosted on a Windows Server 2012, with WFast CGI module bridging the Flask API and the IIS server. For the network, the connection timeout is set to 5 minutes, max bandwidth and max connections are set to 4 GB, and max URL segments are set to 32 pieces. The paper also explores serverless computing using AWS Lambda and AWS API Gateway for the ML application serverless implementation. The applications are set up under x86-64 architecture with Python 3.9.1 environment. The inference function is coded as the Lambda function, and a root img_classify is defined as a trigger in the API gateway. 2 experimental environments are set up with 2 GB and 3 GB memory, and the timeout is set to 50 seconds. The ML application is transferred as a Docker container, and the runtime of the TensorFlow keras is defined inside the Docker file. For containers, the paper follows the Docker files on NVIDIA's official repository to set up a virtual environment in the existing Windows server. The exception model is used as the base model to test different implementation environments. The model requires a minimum of 110.9 MB for storage, and the inference overhead is 109.4 ms. The experiment uses an open-source training dataset containing 4,000 images, split into 80% for training and 20% for validation. For model development, the paper focuses on accuracy and loss of the trained model. For model deployment, it cares about session length, response time, and failed rate when placing ML application requests in different computing platforms. The model training is performed using Google TensorFlow, with a 20-fold cross-validation technique to evaluate the models during training. The training dataset is divided into 20 subsets, with 16 used for training and the remaining 4 used for testing. Figure 3 compares the CPU and GPU clusters' accuracy and loss, showing that both models reach 99% training accuracy and 70%-80% validation accuracy and around 0.9 validation loss after 20 epochs. The CPU cluster takes 910 epochs to get the final stable accuracy and loss, while the GPU cluster takes 12 epochs to reach a final and stable accuracy. This section presents the performance evaluation of a Flask API server implemented on a local web server, in-house data center, and AWS Lambda serverless environment. The authors conducted load tests using a cloud-based performance scripting client, Artillery, to generate request loads with varying frequencies and data sizes. Load test results for the local web server and in-house data center are shown in Figure 4. Both platforms exhibit similar failure rates, peaking when total sessions reach 1300. The session length surges on the local web server at 1200 total sessions, whereas it increases on the in-house data center at 1400 total sessions. This difference is attributed to the single-threaded implementation of the ML application on the web server. Figure 5 presents the results for the same exception application implemented on AWS Lambda with 2 GB and 3 GB provisioned memory. The failed rate is directly impacted by the provisioned memory, with the 3 GB provisioned memory outperforming the 2 GB provisioned memory. The application latency remains relatively unaffected by load changes, with a median response time of around 300,500 milliseconds even when the request frequency increases up to 6,000 per 180 seconds. Figures 6 and 7 compare the failed rates of different compute platforms, including Flask Local, Flask On-Premise, Docker 2 GB, Docker 4 GB, AWS 2 GB, and AWS 3 GB. The results show that serverless computing exhibits an acceptable failed rate as the request frequency increases, and that increasing the provisioned memory from 2 GB to 3 GB for serverless computing decreases the failed rate. Figure 8 presents a comparison of the response times of the different compute platforms. The Flask API outperforms the RESTful implementation in terms of response time. The results demonstrate the improved performance of the hybrid infrastructure, particularly with the use of serverless computing. Overall, the authors highlight the advantages of serverless computing in terms of failed rates and response times, particularly when provisioned memory is increased. StraightLine is an end-to-end resource-aware scheduler that optimizes resource allocation for machine learning applications in hybrid infrastructures. Traditional machine learning systems focus on a single stage or phase of the ML application lifecycle, often assuming homogeneous infrastructure, which may not reflect real-world scenarios. In contrast, StraightLine leverages Docker to containerize model development stages, offering plug-and-play provisioning. The proposed empirical dynamic placing algorithm intelligently places requests based on their unique characteristics, such as request frequencies and data sizes. Preliminary experiments demonstrate StraightLine's effectiveness in reducing response time and failure rates. Results show that the Flask API outperforms other computing platforms in terms of response time, thanks to its ability to offer local computation for ML applications. The empirical dynamic placing algorithm plays a crucial role in optimizing resource allocation, as it considers the distinct characteristics of each request. Future directions for StraightLine include evaluating its performance across diverse scenarios and workloads, enhancing the empirical dynamic placing algorithm to consider additional model and application parameters, and refining the scheduler to dynamically allocate resources based on real-time demand fluctuations and workload patterns. The effectiveness of StraightLine depends on the characteristics of the ML applications and the underlying infrastructure. As such, future work will focus on accommodating diverse scenarios and workloads, ensuring the scheduler's adaptability and versatility in real-world deployments.